Thank you for joining us. If you ever dealt with big data, you probably ask yourself how you can ingest terabytes of data and how you can make all this data available for customer-facing dashboards, because in today's world, clients are expecting to get answers in real time. And finally, how you can do all of that in a cost-efficient manner, because organizations today deeply care about bottom line. So you came to the right place, because this is exactly what we're going to discuss today. We've been using Apache Druid for the past 6 years now, and we believe that we have some good answers to the aforementioned questions. So before we start, just a short disclaimer. This presentation mostly covers advanced topics in Apache Druid, but we still believe that it can be useful for broader audience, so no need to worry if you don't have previous experience. If you are looking for an introductory session about Apache Druid, you can check out our previous talk from Big Data London in 2019. And finally, this presentation mostly covers our journey with Apache Druid, while me and Itai worked at Nielsen. So my name is Yakir. I'm co-founder and CEO at Cocoa.ai. And before that, I was leading the engineering for Nielsen Identity. I mainly focus on big data and machine learning solutions. And with me today, Itai, who is currently a senior solutions architect at Databricks. Before that, he was a principal solutions architect at Imply. And before that, he worked at Nielsen as our big data group tech lead. And as you can see, he has been dealing with big data challenges for quite some time. Okay, so what we are going to discuss today. So first of all, we're going to discuss data modeling. And we're going to show you how you should model your data when you're gonna ingest it into Druid. Then we're gonna discuss data ingestion, and we're gonna show you how to ingest terabytes and petabytes of data into Apache Druid. Then we're gonna discuss retention and deletion, because it is very important to know when to delete data from Druid, because you don't want to pay for data that you don't use. And finally, we're gonna discuss query optimization and share with you some tips and tricks on how to improve the performance of your queries. And of course, we're going to show you how to leverage all that knowledge in your organization. Okay, so before we jump into the technical details, some business context. So Nielsen is a data and measurement company. Nielsen is very famous for providing TV measurement, TV rating, especially in the United States. And essentially what Nielsen is doing is collecting anonymous device level and person level data from various sources, online sources, offline sources, panels. And the idea is to create an holistic view of a consumer out of all these pieces of information that are being collected and provide insights on this consumer. So these insights are being used by the different measurement and targeting products in Nielsen. And in Nielsen, we have a very extensive data infrastructure. These numbers here represent only a single division in Nielsen. But as you can see, these numbers are very impressive. We are processing more than 10 billion events on a daily basis on our Kafka clusters. If we're talking about S3, we are storing more than 60 terabytes every day on S3. And in general, our data lake consists of more than 5 petabytes of data. Talking about Spark, we are running more than 6,000 nodes of Spark on a daily basis. And finally, when talking about Druid, we are ingesting tens of terabytes of data into Druid on a daily basis. And this extensive data infrastructure supports many products, as I said, and many use cases. In this presentation, I want to focus on 2 use cases. The first one is what we call building target audiences. So audience in our world is basically composition of attributes. Each device it can be defined by different attributes that we can assign to the person who is using this device. So for example, the gender of this person, the age of the person, the interest of this person. So these are attributes that we assign to a device or to a person. And when talking about audiences, we basically want to allow our clients to define a composition of these attributes. So for example, an audience can be all the females in a specific age with a specific interest. So what you see in the screen here is basically the audience definition screen. our clients can drag from the bottom part of the screen the different attributes, define the relation between them. It can be an AND relation or an OR relation. And our goal is to find the number of unique devices or unique persons and show the number in the blue box at the top. The second use case that I want to discuss is what we call funnel analysis. Marketeers need the ability to measure the effectiveness of different funnels that they're running. Now, in order to measure the effectiveness of a funnel, they need to understand how many people reached each stage in the funnel. So our goal is to analyze each stage and report the number of unique devices or unique persons that exist in each stage. And this is how marketers, again, can understand the effectiveness of the different funnels and compare and choose the best funnels that work for them. So I presented only two use cases, but as you've seen, we have diverse use cases. And we were looking for a single system that can help us solve many different types of data problems. We didn't want to have a dedicated system for each use case, because then it means that our infrastructure will get very complex. So we were looking for a single system. Now Druid, because the extensive query language, the ability to fine-tune the system, to configure it, was a great fit for us. And if you also think about it, there is also a common thread to this problem. Essentially, what we're trying to do, no matter whether we are talking about building target audiences or analyzing a funnel, we are trying to find a number of unique elements, of unique devices or persons in some stream of events. So this is essentially the count distinct problem. And we try to do that in real time because there are users who are waiting on the screen for an answer. So it cannot take minutes to return an answer, and it cannot take even tens of seconds. It's too much. And of course, we need to do that at scale because we need to scan a lot of information in order to generate an answer. Now, unfortunately, if you try to solve the count distinct problem and do that in real time and at scale, you will soon find out that there is no accurate, space efficient, and time efficient solution. So the only relevant solution in our use case was to use what is called approximation algorithms. Now, the idea behind approximation algorithms is that you don't get the exact result. You don't get the exact number of unique elements in a set, in our case. You get some estimation, which should be close enough. But in return for the loss of accuracy, you get significant improvements, both in the time required for the solution to run and in the space required for the solution. So we chose ThetaSketch, which is an approximation algorithm that is based on the idea of KMV, K minimum values, where K is a constant that defines the number of samples you store. Again, in approximation algorithms, you don't need to store all the elements in your universe. You only store a sample. And this is how you also control the space requirements of the solution. And the minimum values refers to the process of choosing which elements you're going to store in your sample. With KMV and ThetaSketch, of course, you can estimate set cardinality, which means that you can get the number of unique elements in a set. And for us, the biggest benefit of ThetaSketch and KMV was its great support for set theoretic operations, which is a very important feature for us because it means that we could calculate intersection and union between two sets or more without losing too much accuracy. And again, this is an important feature because if we are going back to the first use case, building target audiences, essentially what we are doing there is calculating an intersection or union between multiple attributes. Now, the only downside of KMV and ThetaSketch was when we tried to intersect a very small set with a very big set. Only in this specific scenario, the error was relatively high. And Itai will share with you some ideas on how you can mitigate this specific problem. So we know that we want to use ThetaSketch, but we had to find a concrete implementation of ThetaSketch. And luckily for us, ThetaSketch is supported in Druid via the great data sketches library from YAO. And the way that it works is that during ingestion time, based on your configuration, the different sketches are being created and stored as Druid segments. And then during query time, the sketches are being pulled from the segments, aggregated based on the configuration, and you get a final aggregated sketch that represents the number of unique elements in your set. Now, this is a very basic explanation about data sketch and how it works in Druid. If you are looking to understand and learn more and maybe understand how it works behind the scenes, you can watch these short videos that we created a few years ago. Okay, so we learned about the counting problem. We understood that this is a very difficult problem to solve, especially in real time and at scale. And we understood that data sketch can help us and that data sketch is supported in Druid. But now we need to leverage all that knowledge and understand how to build the full pipeline. And this is exactly what Itai is going to show you. Thank you.
Thanks, Yakir. Okay, so Yakir told you about data sketch and Druid, and what we're going to do in the next slides is essentially go through a data pipeline and focus on the main areas that you mentioned earlier. So data modeling, data ingestion, retention, deletion, and query optimization. So starting off with data modeling. Here's a made up example of a data source, or essentially a table in Druid. You probably see it as the required timestamp column. There's a dimension, a string column, which we call audience name, which is basically the audience, as Yakir explained, that we identified on a specific device. Now, I called it a naive approach because if we need to count the number of distinct devices we have for a given criteria, for example, how many tablets were used in a given day, then we kind of have to do not a really full table scan, but an inefficient query that will take a lot of time and resources to complete. Now, a better approach would be to replace this device ID column with a data sketch metric based on the data sketch module that Yakir mentioned. And then if we want to know how many tablet devices were used in a given date, we only need to take this specific metric and extrapolate the approximated number of unique devices used. Now, there is some kind of con to that, right? Because if, for example, we need to intersect a very large set, like tablet devices, with a very small set, like Druid committers, which unfortunately for us, there is only a handful, then intersecting these two data sketch metric will probably result in a very high error rate. One way to mitigate that is to extract the device type into a new dimension. And then if we want to know how many Druid committers were using tablets for a given date, there's no intersection. There's only one specific data sketch metric that we need to take or extrapolate the approximated number of unique devices from. Another thing would be slowly changing dimensions. So for example, let's say we want to change the audience name from football fans to American football fans, because we all know American football and football is not the same, right? And so with the naive approach, if we actually store the audience name, then changing the audience name in this example would require us to either re-ingest the data or find some other hacky way to do that. However, a better approach would be to leverage Druid lookups. Lookups are essentially a mapping between some kind of arbitrary ID, like this audience ID here, and some kind of string like this audience name here. Now, a lookup can exist in a table, in a relational database, in files, or even in Kafka. And then the Druid processes that are used for serving queries will load those mappings or that lookup into their memory and use it when serving queries. Now, our fact table, or essentially our Druid data source, would look this way after changing it. So rather than storing the audience name, we'll only store the audience ID, which is obviously more efficient. And then we can use it to serve queries. Now, you probably ask yourself, that's great, right? But we're talking about serving customer-facing dashboards. And our customers don't know what is this arbitrary ID, and they don't care. They care about the actual audience name. And so the way to actually present the audience name is to either do a join or to use the lookup SQL function and replace the audience ID with the actual audience name. And finally, when we want to achieve what we started off with, meaning changing the audience name, we'll only need to do it in one place. And this is the origin of the lookup table. So to summarize the data model section, we talked about how you can use TetaSketch for fast and efficient count distinct. And we told you need to pay attention to intersections. I showed you how you can leverage lookups to handle slowly changing dimensions. And we also suggest that you check out the schema design page on Druid's website. Now, moving on to ingestion, there are a few methods to ingest data into Druid. There's the streaming or the real-time ingestion you can do from Kafka or Kinesis. And you can also ingest data in batch, either using the Hadoop-based or the native batch ingestion. It might not be a surprise that we chose the Hadoop-based ingestion because, as Yakir mentioned, we started off with Druid quite early on years ago. Now, there are a few reasons why we chose that. First, the technical considerations. Well, when we started off with Druid, the Hadoop-based ingestion was the most mature option. It's also very scalable. So if we have a significant spike or alternatively a significant drop in the volume of our data at any given point in time, we can either scale up or scale down a Hadoop MapReduce cluster to accommodate the new volume of data. The other thing was business requirements. So we are talking about big data trends, right? So campaign trends and stuff like that. So what we really care about are daily trends. And so ingesting the data once a day or even a few times a day was good enough for us. Now, the Hadoop-based ingestion is still being used in large parts of the Druid community. And so we wanted to share a few tips with you. The first one is, many times you'd want to ingest data in parallel from different ingestion tasks from separate Hadoop clusters to different data sources. And so the way to achieve that is using affinity, which is essentially a mapping between a middle manager and a data source. And so it allows you to point your Hadoop cluster to a specific middle manager and ingest to data source A, and then to point a different Hadoop cluster to a different middle manager and to ingest to data source B in the same time. Another thing that comes up quite often is how I can mask sensitive properties such as credentials in ingestion task logs. And you can do that by using the Druid startup logging mask properties. Now, I still advise you to take a look at the ingestion task logs in the first couple of times, because some sensitive information may still be logged even if this is enabled. Now, it's very important to understand that ingestion tasks actually run two MapReduce jobs by default. The first one is called determined partitions. And basically what it does, it goes through the data, and based on the target rows per segment config property, it determines how many shards or partitions or segments, those are kind of used interchangeably, should be produced from the ingestion task. The second one is called index partitions. And based on the number that was generated from the first job, it will actually build those partitions or shards. Now, in some cases, for example, if you know in advance how many data you're expecting, or if the data volume is kind of fixed, you can actually significantly speed up ingestion if, rather than using target rows per segment, you set num shards in advance in your partition spec. And in that case, it will completely skip the determined partitions and only run the index partitions. Now, MapReduce jobs, even with this aforementioned optimization, can still be quite slow. And so another way to optimize them is by pre-aggregating the data in an upstream process, if this is applicable. So for example, what we did, as I showed you earlier in our data pipeline, we have a Spark application that processes the data. And so in that Spark application, we actually write TetaSketch objects based on partial aggregation of data. And then when we ingest the data into Druid, we set the is input TetaSketch config property to true. So Druid knows we're ingesting TetaSketch objects and not raw data. So to summarize the ingestion section, I showed you the multiple options that exist. I explained why we chose the Hadoop-based ingestion and showed you a few ways to optimize your Hadoop-based ingestion, including, for example, using num shards or pre-aggregating the data. There's a very interesting work in progress done by the community, led by the awesome Itai Yaffe, around being able to ingest data directly from Spark into Druid's deep storage, and you can check out this Git issue. After we modeled and ingested the data, it's very important to manage it and retain and delete it properly. And let's see how. So there are three terms you need to be familiar with. The first term is load rules, which determine which segments should be loaded into the cluster, meaning into the local disks of the historical nodes from the deep storage. And this can be done by interval or period, for example, the last 30 days. They also determine how many replicas per segment will be loaded. The opposite of that are drop rules, which determine when segments should be dropped from the clusters, meaning deleted from the local disks, but not deleted from deep storage. And finally, kill tasks are those tasks that permanently delete all information about the segment and completely remove it from deep storage. Now, segments actually have versions. So whenever you re-ingest data or add new data, a new version of the segment will be created. Now, all versions take up space in deep storage. However, only the latest version is actually being used to serve queries. And it's marked with used equals 1 in the metadata store. And what we suggest you do is to specify your kill task interval as wide as possible. Don't be afraid to do that because it will only delete those segments that are marked as unused, meaning used equals 0 in the metadata store. Why is this so important? Let's take a real world example. We had one of our data sources that had a 1 year retention period, meaning we wanted to serve queries up to the last year. Our deep storage is AWS S3. You can see that initially our kill task interval was everything older than 30 days, meaning delete all the unused versions that are older than 30 days. But again, still maintain those versions that are being used for 1 year. And so it took up over 350 terabytes in our deep storage, and it cost us over $8,000 a month. Now, by only changing the kill task interval to delete all unused versions that are older than 2 days, we managed to drop the used storage to only 15 terabytes and the cost per month to only $350. So we are talking about over 95% improvement for only one single data source. Another cool thing you can do is dimension-based TTL. Now, Druid, as probably any other database out there, allows you to do TTL based on some kind of timestamp column, like this timestamp column here. But however, consider this GDPR-like use case, where in this made-up example, we have data from US countries and EU countries like Sweden. And let's say you are allowed to store up to 90 days worth of data from US, but only up to 30 days worth of data from EU countries like Sweden. At the moment, as you can see, we have data older than 30 days for both countries. Now, let's say we also want to add new data into the data source, which essentially what the result we're looking to get is something like that, right? So to delete all the data older than 30 days for Sweden, keep data older than 30 days and up to 90 days for US, and also add data for today for both countries. And the way to achieve that is using the Hadoop-based ingestion with multi-type input spec. That allows you to combine other input specs. So you can take your existing data in your data source and add or combine new data arriving, for example, from S3. Now, in the type data source, you can actually use a filter as part of the ingestion spec to filter in only the data that you want to keep. I know it was a very high-level explanation, but my colleague and I wrote a deep dive blog post about it, and you can check it out in this link. So to summarize the retention deletion section, we talked about load and drop rules. We talked about kill task as a way to permanently delete data. And we talked about the cool dimension-based TTL trick. So after we modeled, ingested, and managed to retain and delete the data, let's talk about queries. So Druid has two ways to query the data, either native queries, which are based on a JSON query language, or Druid SQL. Again, no surprise, we chose the native queries, mainly because Druid SQL didn't even exist when you started off with Druid. However, Druid SQL is expanding rapidly with each version. So for example, the union all operator was added in Druid 0.20, and the most recent Druid 0.22 brought many features and improvements, including the vectorized query engine support for DataSketch aggregator, which means DataSketch queries got a significant performance boost. That's why today, if you start with Druid, you'd want to start with Druid SQL. Now, let's talk about query optimization, and kind of the common thread in our slides were working with DataSketch. So let's see how we can tune DataSketch size for performance. Remember, Yakir mentioned DataSketch and KMV. K is the size of the sample that we take from the incoming stream of events, and this is basically the equivalent to the size that we will use for the DataSketch when querying it. So queries with relatively high size, like 65,000, are heavy on resources, thus they will take more time. If you switch to a more moderate size, like 4,000, it can significantly improve your speed. And this is very useful if your queries have no intersections, so there will be relatively small effect on accuracy. Now, the flip side of that is tuning DataSketch for accuracy. Let's take this, again, real-world example from one of our data sources. You see I'm using the Druid SQL language here. I'm using the approximate count distinct ds theta function, and I provide the name of the theta sketch metric, the name of the data source, and some kind of criteria. Now, the result here was something little over 3.5 million, right? Now, by only slightly changing it and providing a second argument as 65,000 to this approximate count distinct theta function, we got a result that's around 3,000 higher, and I can show you it's more accurate. And why is that? Because this approximate count distinct theta function has an optional second argument of size, which defaults to 16,000. And so without providing anything, we got a result that's close enough and probably faster, but a bit less accurate than when we provided a higher size. Thus, we got a more accurate result. So to summarize the query section, we talked about the two query methods, why we chose native queries, but why you'd probably want to go with Druid SQL. We showed you how you can tune theta sketch to balance between performance and accuracy. And also going back to the same work in progress done by the community, eventually it will also allow you to query data directly from Druid's deep storage using Spark. Okay, so to summarize, essentially what we showed you is how you can ingest terabytes of data, use it for customer-facing dashboards, and do all that in a cost-efficient manner. Just before we wrap things up, a few things we care about. So first of all, Women in Big Data is a worldwide program that aims to inspire, connect, grow, and champion the success of women in the big data analytics field. There are over 17,000 members worldwide, and everyone can join regardless of gender. So we really encourage you to find a chapter near you using this Women in Big Data website. There are a couple of past talks that we gave, including this Druid intro session from Big Data London 2019 that Yakir mentioned, and quite recent funnel analysis with Apache Spark and Druid talk that my colleague and I gave at the latest Data and AI Summit. There are also a couple of blog posts that we mentioned, including the data retention and deletion in Apache Druid, and the second part of that, which is more focused on data deletion. I would also like to mention that Druid Summit is coming up in November 9th and 10th. And also, Druid celebrated its 9th open source anniversary earlier this week. And you can see the Introducing Druid post on Druid website by Eric Checher that originally announced open sourcing Druid back in 2012. That's it for us. We really appreciate your time and you participating and attending this talk today. And we will also really like to get your feedback. So really feel free to reach out to either Yakir or myself via Twitter or LinkedIn and really provide your feedback, insights, or even follow-up questions. Thanks, everyone.
Okay, so today